Hello everybody. In this video we are going to discuss the last method that we can use to calculate the standard heat of reaction, which is using the heat of combustion of reactants and products. So it's going to be very similar to the previous method for calculating the heat of reaction using the heats of formation. But it's going to be using a different term, which is the heat of combustion. So, and as we did last time, we want to understand first what we mean by the heat of combustion. So to understand this, I think this is very easy to understand now. The heat of combustion is the heat that is produced due to the combustion of any material or any substance. And this combustion is an exothermic reaction by definition, and we do the combustion reaction because we want to produce heat. And this combustion reaction produces carbon dioxide, water vapor, if there's carbon and hydrogen in the fuel, which is the most common case. And we calculate the standard heat of combustion. And this is important because the standard heat of combustion is same as the standard heat of formation. It is at 25 degrees Celsius and 1 atmosphere. And let's say, and the heat that is produced from this reaction, it is called the heat of combustion. And the heats of combustion are available in the same table B1. In this column, let me zoom in more. And as you see here in this column, we have the heat of combustion. And again, it has this small superscript of node here, which is the standard conditions. And this footnote here is about the same thing. It's telling you that this is at the standard conditions of 25 Celsius and 1 atmosphere. And it also has the same units of kilojoules per mole. And as expected, they all have negative signs because they are all exothermic reactions. These values are calculated or are tabulated based on some assumptions. First, that all carbon is converted into carbon dioxide, so it's complete combustion, not incomplete, so it has to be complete combustion, and that all hydrogen is producing or converting into liquid water. And this is important. This is liquid water, not water vapor. And this is liquid water because at the standard conditions of temperature and pressure, water is liquid. At 25 Celsius and 1 atmosphere, water is liquid. So this is what we get out of the combustion at the standard conditions. All the sulfur is converted into sulfur dioxide, and all the nitrogen is converted into nitrogen dioxide. So these are the assumptions that we have. So for example, if we want to talk about the heat of combustion of ethyl alcohol, which is ethanol, we have two values here, one for liquid and one for vapor, and we have here the liquid ethanol, so it's going to be the first value, it's negative 1366.91. This is the heat of combustion of liquid. It's here between brackets as liquid, and it means that the change in enthalpy associated with complete combustion of 1 gram mole of liquid ethanol, which is the reaction that we see here, 1 mole of ethanol reacting with oxygen to produce carbon dioxide and water vapor. So this is what we get from this reaction, and we can predict this heat of combustion if we deal with this equation as a normal combustion or a normal reaction. And this is something that we need to keep in mind, that combustion reaction, it's at the end of the day, it's a reaction. So all what we said that applies to the reaction applies to the combustion reaction. It's a special reaction because we know how to write this equation. If you just know what is the fuel that you are burning or the material that's burning, you can easily write the balance equation. You don't have to be provided with the equation. You can just know it and you can balance it, and it's totally fine. But at the end of the day, it's a reaction. So this heat that we get here, it's a heat of reaction, and at the same time, it's the heat of combustion of ethanol, liquid ethanol. So we can use the heat of formation method to calculate the heat of combustion of ethanol by multiplying 2 by the heat of formation of carbon dioxide gas, plus 3 multiplied by the heat of formation of liquid water, minus 1 multiplied by the heat of formation of liquid ethanol, and of course minus 3 multiplied by 0. And this gives us the same value that we have here. So it's a normal reaction, but it's a special case of the reactions. For the heat of reaction, if we want to calculate the standard heat of reaction from the heat of combustion, it's going to be very similar to what we did in the heat of formation method. So but this applies to the reaction that involves only combustible substances. So this is what is important, that and we'll see later why it applies only to combustible substances. And anyways, without going into these details, we can use this equation that the standard heat of reaction is negative, and this is the main difference between the heat of formation method and the heat of the combustion method. In this method, we use a negative sign multiplied by the summation of the coefficients multiplied by the standard heat of combustion. So this is the main difference, is this negative sign. Otherwise, the equation is the same. You just replace the heat of formation by the heat of combustion, the standard heat of formation by the standard heat of combustion. Otherwise, everything is the same. So this is how we can write the equation. It is the summation of the coefficient multiplied by the standard heat of combustion of the reactants minus the product. We will take an example, and this example is going to be nice because we have here more than one thing that we'll do. First, that we will solve this example using the three methods: the Hess law, the first heat of combustion, the heat of formation method, and the Hess law. The second is we will be looking at this from the Hess law point of view, and we will see how the heat of combustion method that we are using to calculate the heat of reaction, or calculating the heat of reaction using the heat of combustion, is an indirect application of Hess law as we did for the heat of formation. There is something I want to let me go back because I think I missed this point. Oops, I'm sorry. Yeah, here. We said that this method is applicable for the combustible materials. So here you would see for this table we have ethyl alcohol, carbon dioxide, and water. You will see that there is no heat of combustion for carbon dioxide. There is no heat of combustion for water, and this is expected. Yeah, these are the products of the combustion. So you cannot burn water. You cannot burn carbon dioxide. It's already a result of the combustion. So if you have any reaction that involves some non-combustible materials, and materials that cannot burn or cannot undergo a combustion reaction, then the heat of combustion method is not possible to use. And again, at the end of the day, this is one other option you can use if you want, or you can use the heat of formation if you want. The heat of formation is more general. You will find heat of formation for all materials, not like the heat of combustion. So anyways, it's an option we are free to use if we want. So for this reaction, that we have the dehydrogenation of ethane to form ethylene. So we want to calculate the standard heat of reaction using the heat of combustion, the standard heats of combustion. So it's easy. We will find here in this table the standard heats of combustion are already tabulated. So what we can do is just pick the data and apply the equation. We have here the heats of combustion. It's important to note the phases, which is easy. In this case, they're all gases. So it will be as simple as applying the equation. So it's the heat of formation of ethylene minus heat of ethane minus heat of formation of ethylene minus heat of combustion of ethane minus heat of combustion of ethylene minus heat of combustion of hydrogen, which is going to be 136.93. So that's it. So this is what we want to calculate. We can use the heat of formation method. So if we use the heat of formation method, what we will do is simply use the numbers from the previous column. The good thing about the heat of formation that hydrogen heat of formation is 0. So it's going to be just two terms. So it's going to be the heat of formation of ethylene minus the heat of formation of ethane. So this is ethylene, 0 for hydrogen, and for ethane it's negative. So we will get the same value. Let's try to do this calculations using Hess law. So we can do this using Hess law by writing equations that we know. So we can write the combustion reaction for each one of them. This is exactly what we did in the previous case for the heats of formation. So you can write the heat of combustion of ethane. We can write the heat of combustion of ethylene. We can write the heat of combustion of hydrogen. And already the heats of combustion are all, it's not the heat, the combustion reaction of ethane, ethylene, and hydrogen, and we know the heats of combustions are already tabulated, which are the same values that we wrote here. These are the same three numbers that we wrote. which are these three numbers. And now we can apply His law. So to reach this equation, we can find this equation by getting reaction 1 minus reaction 2 minus reaction 3. And then we can have all this equation. We have done this more than once before. We will cancel the terms that are repeated. Oxygen will cancel, carbon dioxide will cancel, water will cancel, and we will end up with this equation. So the heat of reaction, it can be produced by the heats of reactions of the three reactions. So it's delta H1 minus delta H2 minus delta H3, which is plus 1, which is minus the coefficient of ethane, plus negative the coefficient of ethylene, plus negative the coefficient of, this is minus 1, this is a mistake, coefficient of hydrogen, and then we can calculate it, and we will reach the same form, which is the negative the summation of the coefficient multiplied by the heats of combustion. So again, this is one other option you are free to use if you want, and again, the heat of formation is more general. We can use the heat of formation method for any compound, and we don't have the restriction on having combustible materials as for the heats of combustion. So this is all for now, and next time we will be discussing the last part of this chapter that we cover, which is going to be the last part of the course, inshallah, which is about the calculation of the enthalpy change on reactive system at conditions other than standard conditions. So this is what we will be doing next time, inshallah. So I'll see you then.